Let's start today chapter 5, stability of linear control system. Okay, among the performance specifications used in design of control system, stability is the most important one. Okay, stability for the control system is most important one. Okay, so we have to be careful for this chapter. Introduction to stability. We learned that the time response of a linear time invariant system is usually divided into two parts, such as the total yt is equal to the transient part of it and also steady state part of it. As you see here, this is the transient part of the total time response, and this is steady state part of the total response. In stable control system, we want from the transient response limit t approaches to infinity ytt should be 0. Okay, limit t approaches to infinity ytt is equal to 0. Okay, this is the stability condition for any function. What about the steady state response? The steady state response is simply the part of the total response that remains after the transient has died out. Stability. What is the stability? What is stability? Stability is if you apply any bounded input to any system and your answer is bounded again, we can say this system is stable. Okay, for the bounded input, the system will reply as bounded output. For example, if the system response is as like that, what do you think? This is stable or not? This system is stable because, as you see here, the time response is bounded. Okay, so we can say this system is stable. What do you think about this system? It is stable or not? Okay, this system is stable again because, as you see here, the time response is bounded again. Okay, what do you think about this? This system is stable or not? This system is unstable because, as you see here, when t approaches to infinity, the system will go to the infinity. So we can say this system is unstable. Let's continue from another example now. What do you think about this system? It is stable or not? This system is unstable because, as you see here, we have increasing type of oscillation for the time response. So we can say this system is unstable because of the increasing oscillation. Time approaches to infinity, we can say this system will go to the infinity. Okay, so we don't have bounded output. Okay, so what about this signal? It is stable or not? What about now? As you see here, we have the same amplitude oscillation for the time response. What can we say? This system is stable or not? This system is marginally stable or marginally unstable. Okay, both of them are correct. This system can be stable or unstable with respect to the input. Okay, let's continue now. After all, we can say BIBO means bonded input, bonded output is stability. Okay, we can say BIBO stable or this system is stable. This is another definition for the stability. Okay, the roots of the characteristic equation or the poise of the transfer function cannot be located in the right half S-plane or on the imaginary axis. I will show you on the S-plane. Okay, this is the real part of the roots, real axis. This is imaginary axis. Okay. For the stability, the roots of the characteristic equation or the poise of the transfer function cannot be located in the right half S-plane. It means we don't have to root of the right half of the S-plane for the stability. And also, we don't have to any roots on the imaginary axis such as here and here. Okay, for the stability we have roots on the left side of the S-plane in here. When a system has roots on the imaginary axis, we can say this system is marginally stable or marginally unstable. Why? When you apply a sinusoid function to the input, for example, if ut is sine omega 0 t for the marginally stable system, for example, the roots of the system is s is equal to j omega 0 and s2 is equal to minus j omega 0. We know this in this condition, the roots on the imaginary axis, so this system is marginally stable or marginally unstable. When you apply an input as sinus omega 0 t, the system response will be function of the t sine omega 0 t. You can get it from the Laplace and inverse Laplace table. So what can we say about this time response now? This is stable or unstable? Let's evaluate the time response of this system. If you evaluate this system when t approaches to infinity, what can we say? Of course, it will go to the infinity, right? Because as you see here, we have a t here. What is t? T is time. So time approaches to infinity, the function will be goes to the infinity. So we don't have bounded output. This system is unstable. Okay. Maybe we can summarize in a table stability condition now. Stability condition. According to the root values, we can say asymptotically stable, simply, or we can say or simply stable when if the all real parts of the roots is less than 0. Okay, for all roots. In this condition, all roots in the left half S-plane. So we can say this system is asymptotically stable or simply stable. We can say marginally stable or marginally unstable. When the root, any root, has no real part, okay, has no real part, and we don't have any other roots which greater than 0. In this condition, we can say marginally stable or marginally unstable. Sorry about that. We have another condition, which is we don't have multiple order roots on the imaginary axis. Okay, in this condition we can say the system marginally stable or marginally unstable. The real part of any roots is 0 and the other root, the other any root is greater than, not greater than 0. Sorry, we have to write here no, and also here we need no. We don't have any multiple order roots on the imaginary axis, so we can say this system is marginally stable or marginally unstable. What about instability? If we have any root which has a real part greater than 0, we can say directly this system is unstable. Or if we have multiple order roots on imaginary axis, so we can say again this system is unstable. So the stability of linear time invariant single input, single output systems can be determined by checking on the location of the roots of the characteristic equation of the system. Okay, this is the condition for us. If we summarize again on the S-plane, this is real part and imaginary part. We can say directly this part unstable region. Again, in this region, the system will be again unstable, but left half plane on the system, we can say stable region, and again stable region. That's all. It is so simple to analyze the stability. Okay, let's do some examples now. What can you say about ms is equal to 20 over s plus 1, s plus 2, s plus 3. What can you say about this system? It is stable or not? Yes, all of the roots on the left half S-plane, so we can say this system is stable. Okay, what about the others now? 20 times s plus 1 divided by s minus 1 s squared 2s plus 2. What about this? This system is stable or not? This system is unstable because of the s is equal to 1 is a root of this system. So this root will be on the right half S-plane. So this system will be unstable. Okay. What about the others now? 20 times s minus 1 divided by s plus 2 times with s squared plus 4. What can you say now? This system is stable or not? Okay, let's analyze the roots of this system. In here we have a root from at minus 2. Another root s2 and 3, we can say plus and minus 2j. So this system will be marginally stable or marginally unstable because of the imaginary roots. Okay, what about the last one here? 10 divided by s plus 2 s squared plus 4 to power of 5, for example. What can you say now? This is marginally stable or marginally unstable. What about the last one now? What is the rule? Let's check it now. The system will be unstable when if any root has greater than 0 or multiple order roots on imaginary axis. Okay? In this condition, this system will be unstable. It is about the imaginary axis, okay? Not the real one. In this question, as you see, we have related with the imaginary axis, so we can say this system is unstable because of the multiple order roots on the imaginary axis. Okay, unstable. To determine the stability, we have some methods to analyze the systems. Methods of determining stability. We have three methods to analyze the system stability. The first one is Routh-Hurwitz criterion. This method is an algebraic method to analyze the system stability. Okay, this is an algebraic method. Today we will learn this method. The other one, Nyquist criterion. This is semi-graphical methods to analyze the stability again. If we have enough time, we will learn this method also on chapter 10. And the last one is the Bode diagram. Yes, with this method we can analyze the system with respect to the magnitude and phase diagram. Okay, this system is also graphical method. We can analyze the magnitude and phase diagram with the Bode diagram. We will learn Bode diagram if we have enough time on chapter 10. Today we will learn Routh-Hurwitz criterion. Now we can start Routh-Hurwitz criterion. Okay, consider that the characteristic equation of a linear time variant single input, single output system of the form of Fs is equal to an Sn plus an minus 1 Sn minus 1. It will continue as like that. A1s plus A0 is equal to 0. This is the characteristic equation of the system. For this system, if all coefficients which are an, an minus 1 and blah blah a1 and a0 are real, not have any imaginary part, we can evaluate this function by using the Routh-Hurwitz criterion. Okay, it is needed to analyze any system stability according to this rule. All coefficients should be real, not imaginary. Okay, in this condition we have two criterion: necessary condition and sufficient condition. For the Routh-Hurwitz criterion, we need necessary condition and sufficient condition. Okay, necessary condition is about the coefficients. All coefficients given above should be the same sign. In here, for this equation, all coefficients which are an minus 1, blah blah, a1, a0 should be the same sign. Okay, if one of them is minus, all of them should be minus. If one of them is positive, all of them should be positive. Okay, the other necessary condition is none of the coefficients should be vanish. It means none of the coefficients should be zero. Okay, these are necessary conditions to evaluate the stability of the system by using the stability. And then if any system satisfies these two conditions, we will analyze the system according to the sufficient condition. What about the sufficient condition? First of all, we have to establish Routh tabulation for the sufficient condition. Let's start to the Routh tabulation. For the Routh tabulation, the first step in the simplification of this criterion to arrange the coefficients of the equation into two rows. In here, for example, we have a characteristic equation. First of all, we have to create two rows according to the coefficients of this system. We will start always the higher order S value. So in this equation, the higher order one has an. So we will start from an to create the first row, and then we will continue from an minus 2, an minus 4. It will continue until a0. This is the first row of the Routh tabulation. The second row will be the missing term, which are an minus 1, an minus 3, an minus 5, and it will continue until the last one will be 0, of course. This is the first step to create the Routh tabulation. The next step will be explained on an example now. Let's think about this system. A6 plus s to the power 6, a6 s to the power 6 plus a5 s to the power 5. It will continue a1s plus a0. This is the Fs, which is characteristic equation of a system. Let's create the root tabulation now. The first clone will be as an order of them. The higher order component is s to the power of 6, as you see. So we will write s to the power of 6 and then s to the power of 5. This is the first clone for us. S to the power of 0. Until s to the power of 0, we have to write. This is the first clone of the root tabulation. And then we will continue starting from the higher order component. It is A6, as you see here. A6. And then A4. It will continue A2 and A0. Okay. What about the second row now? A5, A3, A1 and 0. Okay. We will determine the other components of the root tabulation with respect to the first two rows. Okay. For example, in here we will find A value, B, C. Please be careful about this. If you find any 0 value from anywhere, the consecutive component of this clone will be again 0. Okay? So, in here we have a 0. The other terms will be 0. Let's continue now. This should be D, for example, E, F. We will find all of them. G, H, L, M, N, P, R, S, and T. Okay, let's start from A value. A will be calculated as A5 times A4 minus A3 times A6 divided by A5. Okay. This product minus this product over by A5. Okay. We can find A as like that. What about B? B can be calculated as A5 times A2 minus A6 times A1 divided by again A5. For the same row, division part will be always the same. Okay? What about C now? C will be equal to A5 times A0 minus 0 times A6 divided by A5. So it will be A0. Okay, we can write it here directly A0. Okay, let's continue now from D. What about D? D will be equal to A times A3 minus B times A5 divided by A. Let's continue from E. E will be equal to A times A1 minus A5 times A0 here divided by A. Okay, what about F now? F will be equal to A times again 0 minus A5 times 0 divided by A. So it should be 0. In here we find a 0, so the consecutive clone components will be 0. We can directly write it. Okay, let's continue from G now. What about G? G will be equal to D times B minus E times A divided by D. And H will be equal to D times A0 minus A times 0 divided by D again. So it will be A0. For the H, we found A0. Okay, what about the M? Let's find it. M will be equal to here G times E minus A0 times D divided by G. And N will be equal to G times 0 minus D times 0 divided by G. It will be 0. Yes, we found another 0 here. The consecutive component will be as 0. We can directly write it. So what about the last one, which is our M times with A0 minus 0 times G over by M. It will be A0. Here we have another A0. Okay, that's all. What about now? Until now, only we have some calculations. After all of these calculations, we will analyze the first clone now. We will analyze the founded first clone. If we have here any sign changing, so we can say this system is unstable. If we don't have any sign changing, so we can say this system is stable. That's all. The Routh-Hurwitz criterion can be explained as like that. In this clone, if we have any sign changing, so we can say the system is unstable. But if we don't have any sign changing, so we can say the system is stable. For example, assume that A6 is positive, A5 is positive, A is negative, D is positive, G is positive, M positive, A0 is positive. What can you say? This system is stable or not? In here, we have another important issue is that the number of the sign changing gives us to the number of the roots on the right half S-plane. Okay, this is important. For this example, we have two sign changing, so we can say we have two roots on the right half S-plane. So this system will be unstable. That's all. This method is so easy to analyze it.